Okay, so now we're going to use something called an ice chart to calculate equilibrium partial pressures when you don't start at equilibrium. Suppose you start out with only water in a rigid container at 25 degrees Celsius, and its initial pressure is to be recorded at 0.784 atms. That's initially, at the very beginning. You are not at equilibrium. What are the partial pressures of each species going to be when you do reach equilibrium? And then it gives you the Kp value of 2 times 10 to the negative 42nd, which by the way is freakishly small, which should mean that equilibrium tends to favor the left-hand side. Okay, so the first thing you do is you write your reaction out, and then underneath it you're going to make something called an ice chart. An ice chart, I stands for initial at the very beginning of the reaction, C stands for change, E stands for equilibrium. Initially, before this reaction took place, I had 0.784 atms as far as pressure for water. Okay? Since this reaction has not taken place yet, over here on the right-hand side, I have 0 pressure for hydrogen and 0 pressure for oxygen gas. Now, what change is going to take place? These are my reactants, so they're going to have to decrease, so I have a negative value here. These are my products. They start with 0, so they have to go up, so these are going to have a positive right here. And then notice that oxygen is going to gain, I don't know, so I call it X. Hydrogen is going to gain 2X because of the coefficient. And therefore water will lose 2X. So then 0.784 minus 2X, 0 plus 2X, 2X, 0 plus X is X. And now I can plug these equilibrium concentrations into the equilibrium expression. If you remember, for the expression for this, Kp is going to equal the pressure of hydrogen squared times the pressure of oxygen divided by the pressure of water squared. If I plug those values in that I got from my ice table, 2x squared times x over 0.784 minus 2x squared. Now here's a little trick. When the equilibrium constant is small, freakishly small, smaller than 1 times 10 to the negative 4th, you can ignore this x and get rid of it. Okay? So notice right here they took it off. 2 squared is 4, so that's going to be 4x squared times x, which is 4x cubed. They got rid of the minus 2x right here, and now I can solve for x. When I solve for x, I get 6.7 times 10 to the negative 15th atms. That's just x. Remember, hydrogen is going to be 2x, or 1.3 times 10 to the negative 14th. Water is going to be 0.784 minus, and remember it was minus 2x, but this number is so small that if I take 0.784 minus 2x, it's still pretty much 0.784. So number one, 1.3 times 10 to the negative 14th, which is my value for 2x, is so small that 0.784 minus that number, it would still be 0.784. Also, K is smaller than times 10 to the negative 4th, therefore it's okay to just void out that minus 2x. Let's try another one. This time we're going to do it with concentration, so we're going to do Kc instead of Kp. So where it says find the equilibrium concentrations of all the species if 0.194 moles of COCl2 is allowed to come to equilibrium in a 5.8 liter container at 25 degrees Celsius. They give us the Kc value of 7.27 times 10 to the negative 38th. This right here tells me that K is freakishly small, which means it favors the left-hand side, the reactants. It also means to me that if I'm going to be subtracting an x, I could probably just void out that x and take that shortcut. The first thing I notice is I have moles and liters, and I'm talking about concentration. So I'm going to have to do this in molarity. So I take 0.194 moles divided by 5.8 liters to get 3.3 times 10 to the negative second molarity. Now I have my brackets, my concentration. I'm going to fill out my ice chart. So initially I have a value right here, 3.3 times 10 to the negative second molarity. Since this is initial, my products are 0. This side's going to gain gain, this side is going to lose. So down here we're going to have 3.3 times 10 to the negative second minus x. 0 plus x is x, 0 plus x is x. I'm going to plug these values right here into my Kc expression. Kc for this would be the concentration of carbon monoxide times chlorine divided by CoCl2. So now I plug in my values, x times x, which is x squared, 3.3 times 10 to the negative second minus x, and this number is going to be so small that I can just get rid of that step. It makes the math a lot easier. Otherwise, you have to do the quadratic. When you solve for x, you get 4.9 times 10 to the negative 20th. So CO and chlorine are both 4.9 times 10 to the negative 20th. 3.3 times 10 to the negative second minus that number is still pretty much 3.3 times 10 to the negative second. Okay? This value right here is smaller than times 10 to the negative fourth, therefore we were allowed to get rid of that negative x. For those of you that are not going to be here tomorrow because of the PSAT, you need to try and finish the rest of that packet, which is 1 through 12. You should have 1 through 6 already finished. Now you need to work all the way to 1 through 12. That's what we're going to do in class today.